Estimating 3D geometry from 2D images is a fundamental problem in computer vision. Stereo matching is a solution that identifies matching correspondences. With the development of deep learning, stereo matching networks have shown impressive performance on various benchmarks. A major obstacle to their applications is the high cost of collecting real-world annotations. To make up for the lack of real data, existing networks are commonly pre-trained on synthetic data. With recent advancements in building domain-generalized networks, they have demonstrated strong robustness to unseen domains. However, fine-tuning pre-trained network real-world scenarios significantly damages their domain generalization ability. The degradation of robustness to unseen scenarios can render stereo matching networks unreliable for real-world applications. We compare the fine-tuning of pre-trained networks using ground truth and pseudo-label. Contrast observations lead us to believe that the difference between ground truth and pseudo-label contains valuable information. We observe a significant degradation of domain generalization ability during ground truth fine-tuning, occurring at an early stage. In contrast, there is no substantial degradation in domain generalization ability when using pseudo-label. We divide pixels into consistent and inconsistent regions based on the difference between ground truth and pseudo-label. Ground truth and pseudo-label of the consistent region are similar, otherwise, it is defined as the inconsistent region. We empirically find two primary causes that degrade domain generalization ability. In the inconsistent region, new knowledge without sufficient consistent region for regularization seriously degrades the domain generalization ability. In the consistent region, stereo matching networks can still overfit the details of ground truth. The core idea of our method is to dynamically adjust the learning of different regions of ground truth and pseudo-label based on what networks have learned during fine-tuning. DKT employs three same initialized networks: the student, teacher and exponential, moving average, EMA, teacher. FNEGT removes the inconsistent region of ground truth to avoid them dominating fine-tuning with a probability, and adds fine-grained permutations to ground truth which prevents the student from overfitting ground truth details. FNEPL removes the inconsistent of pseudo-label, and combine the EMA teacher's prediction and pseudo-label to get improved pseudo-label. Training loss is a weighted sum of disparity loss, with the improved ground truth and pseudo-label. Compared to other methods, DKT demonstrates reasonable predictions for weak texture regions. We evaluate how these models generalize to driving stereo, which contains unseen driving scenarios with challenging weathers. Among these published models, DKT achieves the strongest robustness by considering for challenging weathers. We evaluate if these models can generalize well to unseen domains. We see that DKT is the only method that can generalize well to these scenarios after fine-tuning. Using our DKT framework to fine-tune networks achieves competitive target domain performances compared to the baseline fine-tuning. Moreover, DKT can help networks generalize knowledge learned from the challenging booster data to unseen real-world scenes, improving the performance on Kitty and Middlebury than the synthetic data pre-trained model.